Okay, in today's video, we will be looking at the reaction of haloalkanes. So an haloalkane is simply an alkane with an halogen. So halo is coming from the word halogen. And we know halogens are in group 7. Fluorine, chlorine, bromine, iodine. So these are our halogens. So we are looking at haloalkanes, an alkane with a halogen attached. And we are continuing with reaction mechanisms. So we are looking at reaction of haloalkanes. When alkanes react, the mechanism by which they do so, it's a substitution reaction. So haloalkane, we are still dealing with alkanes. Therefore, the reaction is still substitution. When it was strictly an alkane, the mechanism was free radical substitution. So the halogenation of alkanes, that is called free radical substitution. But now we are looking at the reaction of haloalkanes, and that reaction, the name of the mechanism is called nucleophilic substitution. So as the name suggests, nucleophilic substitution, it means that we are going to substitute one nucleophile for the next one. So remember, a nucleophile is anything with what? A negative charge or a lone pair. The chloride ion, it has a negative charge, therefore it's a nucleophile. If you look at water, there is no charge. However, the oxygen has lone pairs on it. So once it has a lone pair, it is a nucleophile. When you look at the molecule of water, we don't put the lone pair on it, but you should know that the oxygen atom has lone pairs of electron. So the fact that the oxygen atom has lone pairs, it is a nucleophile. So, nucleophilic substitution, we will be substituting one nucleophile with the next one. Before we look at the mechanism, we are going to look at what is a carbocation. So you must know what is a carbocation. Cations are ions with a positive charge. Carbocation, it means that it's a carbon atom with a positive charge. For example, let's say we have a carbon to chlorine bond. We know that chlorine is electronegative and the carbon is not. What does that mean? The bond between carbon and chlorine is polarized. That means the chlorine is slightly negative, the carbon is slightly positive. Remember when we were doing reaction mechanisms, and we said that a covalent bond like this one, it will break in two ways, either homolytically or heterolytically. If the bond is nonpolar, like the carbon to hydrogen bond, the distribution of the electron is even, so there will not be any charge on the molecule. So this bond is nonpolar. when you have a non-polar covalent bond, if it is broken, it will be broken homolytically, and therefore each atom in the bond will get one electron. However, this bond is polar. When you have a polar covalent bond and it breaks, it will break heterolytically. That means one atom, specifically your electronegative atom, will gain both of the electrons. So if you have a carbon atom bonded to an electronegative atom, and the bond is going to break, it will break heterolytically, and your halogen will get both of the electrons. Now, when your bond breaks homolytically, what is formed? We get radicals. Remember, we said that when a bond breaks homolytically, each atom gets one electron, so that is a radical. An unpaired electron, that's a radical. However, when it breaks heterolytically, we will end up with what? An electrophile and a nucleophile. So you get your positive carbon ion and your negative chloride ion. Once you have a negative charge or a nucleophile, once you have a positive charge or an electrophile. So this is a carbocation, a carbon with the positive center, positive charge. So this is how you get a carbocation. Now we classify the carbocations as primary, secondary, and tertiary. So let's do an example. This is chloromethane. It is a haloalkane. When the halogen comes off, right? So if chlorine comes off, the bond is breaking heterolytically. When you look at this carbon atom, when you look at this carbocation, the carbon with the positive charge, if you look what is attached to it, you see 3 hydrogen atoms. There are no other carbon atoms attached to it. If there are no other carbon atoms attached to it, it is called a primary carbocation. So this is a primary carbocation. Let's do our next one now. Or we just say it's, or just use the symbol, the 1 degree, to mean primary. Now, if you look at this carbocation, right, it has a next carbon atom attached to it. This one, only hydrogen was attached, so it's primary. This one have 1 carbon atom attached, so it is. This one is also primary. Because this is methane, this is the only alkane with no other carbons attached. This one has 1 carbon atom attached. It is also primary. So if you don't see any carbon attached, which will only be the case of methane, CH4, Once you see one carbon attached, it is primary carbocation. Let me just go check to see if this picks up with the video. Okay. Right. So if you see one carbon atom attached to the carbocation, that's a primary carbocation. So what you must do, pay attention to the carbon to halogen bond. Right? So you are looking at what is attached to the carbon atom bearing the halogen. If it's just one carbon attached, when the halogen comes off, it's a primary carbocation. So this is your carbocation. This is your carbocation. It has one carbon attached, so it's a primary carbocation. If you look at this one now, let's highlight the carbon to halogen bond again. How many carbon atoms are attached to the carbon atom bearing the halogen? We see one carbon atom here, and we see a next one up here. So this is one carbon atom, this is the next carbon atom. So we see that two carbon atoms are attached to the carbon bearing the halogen. So when two carbon atoms are attached, it's a secondary carbocation. So over here, one carbon atom is attached. Only one carbon atom is attached to your carbocation. So it is primary. If you look at this one now, if you look at this carbocation, two carbon atoms are attached. Therefore, that's your secondary carbocation. Again, highlight your carbon to halogen bond. How many carbons are attached to the carbon of the halogen? 1, 2, 3. 3 carbon atoms are directly attached to the carbon bearing the halogen. That is, so when the halogen comes off, it will form a tertiary carbocation. When the halogen comes off, it will form a tertiary carbocation. So let's look at it. Good. 3 carbon atoms are directly attached to the carbon bearing the halogen. So that is a tertiary carbocation. So we know how to identify the tertiary, the secondary, and the primary. Good. So now that we have looked at how we get the different types of carbocation, we are going to look at nucleophilic substitution. The reason why I showed you the different types of carbocation, because based on the type of carbocation formed, it will select a specific pathway for the reaction. So we have two types of nucleophilic substitutions. We have SN1 and we have SN2. If the carbocation is stable, so yes, the secondary carbocation and the tertiary carbocation, those are more stable, and so they will do SN1. So secondary and tertiary carbocations will do the SN1 mechanism, and the primary carbocations will do the SN2 mechanism. So we're going to start with SN2. So in nucleophilic substitution, we will have our HaloAlkane. Alright, so let's say we have chloroethane and we react it with sodium hydroxide. We are going to get ethanol. Let's look at what happened here. This is our HaloAlkane. The chlorine is, remember the chlorine will have lone pairs. So this is our nucleophile. It is electron rich. Remember, it is pulling the electrons towards itself, so it will have a high electron density. This sodium hydroxide, the solution of sodium hydroxide, right? When you put sodium hydroxide, when you dissolve it in water, you will have sodium ions. So when you have this solution of sodium hydroxide, the sodium hydroxide, it will dissolve, so you will have sodium ions and you will have the hydroxide ions. Good? So it's not the entire sodium hydroxide. Remember I said that the equation does not give you the full picture of the reaction. That is why we do mechanism, which is a more detailed process. So it's the hydroxide ion of the sodium hydroxide that will actually react with your HaloAlkane. Now the chlorine will come off, right? So if you have sodium ions and chloride ions, they can combine with each other to give you the sodium chloride. Okay. Let's look at the actual mechanism now. Remember, when you dissolve sodium hydroxide in water, the sodium and the hydroxide ion will break apart. So you will have the hydroxide ion available. It is a nucleophile. So your hydroxide ion, right, is a nucleophile. Remember, your oxygen, it has lone pairs of electrons. This carbon to halogen bond, as I showed you earlier, it is polarized. That means this carbon is slightly positive and the chlorine is slightly negative. Nucleophiles are always seeking out positive atoms to attack. Remember the word attack? When we say it is looking for something to attack, it is trying to form a bond. So the nucleophile is always looking for positive centers to attack. This bond is polarized because the chlorine is pulling the electrons towards itself. So yeah, nucleophile now, if it wants to form a bond, it has to form a dative covalent bond. A dative covalent bond is when one atom donates both of the electrons towards the bond. Remember, every bond that is formed, it needs 2 electrons. So the hydroxide ion has a lone pair, so it can donate it to the carbon atom to form a bond. So it is doing a direct attack on the carbon atom. When a nucleophile attacks the carbon atom bearing the halogen, right, you cannot attack this carbon atom because this carbon atom is positively charged. Nucleophiles attack positive centers. The reason why this is slightly positive is because it is forming a direct bond with chlorine, and the chlorine is pulling the electrons from it. So this will be slightly positive. So you must ensure that when you're doing the nucleophilic attack, we are attacking the carbon atom that is directly attached to the halogen. Once you attack the carbon with the halogen attached, your halogen will come off. So the bond between the carbon atom and the halogen will break heterolytically. Remember, once you have a polar bond, it will break heterolytically. So what is happening here? We have a bond that is being formed between the carbon atom and the nucleophile, and the bond is being broken between the carbon atom and the halogen attached. So the bond between the carbon atom and the halogen is being broken, and the bond between the carbon atom and the nucleophile is being formed. This we refer to as our transition state. So look, nucleophile attacks the carbon atom when the halogen comes off, right? This now we are showing it as the bond is being broken, and as the bond between the nucleophile and the carbon is being formed, and the bond between the carbon and the halogen is being broken. We call this state the transition state. Now, this reaction is a concerted reaction. It means that as the bond is being formed between the nucleophile and the carbon, the bond between the carbon and the halogen is being simultaneously broken. It's a one-step reaction. So what will happen next is that this bond will be completely formed and this bond will be completely broken. So I'm just going to continue by drawing the next arrow, and then we will do this. So, look again. The halogen attacks the carbon and the chlorine comes off. The transition state, we are showing the bond being partially formed and partially broken. So we use broken lines to represent the bonds being partially formed and partially broken. And then, eventually, the bond between your nucleophile will be completely formed, and the bond between the carbon and the halogen would have been completely broken. And so the chloride ion would have come off. The reason why we have the negative charge here, the chlorine atom, it gained both electrons from the bond. And that's it. All we're doing is substituting your halogen with a nucleophile. That is nucleophilic substitution. We are substituting one nucleophile for a halogen. That's it. So that is SN2 mechanism. Alright, we're going to do SN1 mechanism. As we said, SN1 is for secondary and tertiary carbocations. Again. So again, we are going to replace our halogen with our nucleophile. Unlike SN2, which occurred in a single step, right? The SN1 mechanism, it has two steps. And step one is the formation of a carbocation. So the first thing that will happen is that the halogen will leave. And remember, carbon to halogen bond polarized, so it breaks heterolytically. So in step one, we have the formation of the carbocation, and that happens when the bond between the carbon and the halogen is broken. And this step is known as the rate determining step. So the reaction mechanism, it has two steps, right? This step is called the rate determining step because it determines the overall speed or the overall rate at which the reaction occurs. So when you have two steps in a reaction mechanism, two or more steps, the slowest step is called the rate determining step. So we have two steps. Right? So the formation of the carbocation is the slower step of the two. So it is called the rate determining step. And also, that is what we call it SN1. So the rate of the reaction is only dependent on your haloalkane. So the SN1, it means the rate of the reaction is dependent on your haloalkane. In SN2, the rate is affected by both the haloalkane and the nucleophile. So SN2 rate is affected by the nucleophile as well as the haloalkane. So SN2, in terms of the rate, bimolecular. So both of them affect the rate. And then because it's there, haloalkane, so only the haloalkane affects the rate in SN1, but in SN2, both the haloalkane and the nucleophile affects the rate. So it's bimolecular. SN1, unimolecular. So back to the mechanism. Step one, formation of our carbocation. Once we form our carbocation, then we should know what happens next. Nucleophiles are always seeking out positive centers. So let's draw back our carbocation now. Alright, so in step 2, let us annotate. We will have our nucleophilic attack. Nucleophilic attack on the carbocation. So let's draw our carbocation. And our nucleophile is the hydroxide ion coming from sodium hydroxide. Remember, we draw the arrow, the curved arrow from the source of the electron to where it is forming the bond. So our nucleophile is attacking the carbocation. OH, functional group for alcohol. So you can get an alcohol from an HaloAlkane by doing nucleophilic substitution. You can get an alcohol from an alkane, so you also have reaction schemes as well. How you move from one functional group to the next. So if you have an alkane, you could halogenate the alkane and you will end up with an HaloAlkane. So if you have ethane, you could do halogenation and get chloroethane. Once you have chloroethane, you react it with sodium hydroxide and you get ethanol. So you can get an alcohol from an alkane. And that's your mechanism. So let's go back step 1, formation of the carbocation. First, look at the HaloAlkane again. We see that the carbon bearing the halogen, the carbon with the halogen, it has 3 carbons attached. So it is a tertiary carbocation. That means the mechanism we have to do is SN1. In SN1, the first thing we do is form our carbocation. That means your halogen has to come off. Bond between carbon and halogen breaks heterolytically. And so you end up with an electrophile and a nucleophile. This step is the slowest step of the 2, so it is the rate determining step. In step 2, we have nucleophilic attack on the carbocation. So your nucleophile will attack the carbocation, and you draw a curved arrow from the lone pair to the carbocation, and you get your alcohol, and that is SN2. SN1. Now, sometimes water will also act as your nucleophile. Sometimes water will act as your nucleophile, and that is called hydrolysis of HaloAlkane. It is still nucleophilic substitution. So in the hydrolysis of HaloAlkane, water acts as the nucleophile. So let's look at the example. So let's do chloroethane again. So water will use its lone pair to attack the carbon bearing the halogen. And the bond between the carbon and the halogen will be broken heterolytically, just as before. And so we will have our transition state, where the bond between the carbon and the halogen is being broken and the bond between the carbon and the nucleophile is being formed. And this is our transition state. From the transition state, we know that the bond between the carbon and your nucleophile will be formed, and the bond between the carbon and the halogen will be completely broken. Now, in SN2, it's normally just a single step, right? We would end here. But when it's hydrolysis of HaloAlkane, it's 2 steps. So this is step 1. In the second step, the water molecule is going to act as a base. A base is a proton acceptor. So our next water molecule will come and remove a proton. So in this step, water acts as a base to remove a hydrogen ion or a proton. To remove a hydrogen from the water molecule of the water molecule, remove hydrogen from the water molecule that was attached. Or let's say that acted as the nucleophile. To remove a hydrogen from the water molecule that acted as a nucleophile. And so what we will have now is this. When you have a next molecule of water, so this is our product from here, water, and next water molecule is going to remove a proton from the water molecule that acted as our nucleophile. So this is the molecule of water, H2O, that acted as our nucleophile. So this is the water molecule acted as our nucleophile, so it has now formed the bond with carbon. So it is going to remove, so we are now moving a proton from this molecule of water. So you get what? An alcohol and the hydroxonium ion. Remember you have H2O and you gain the next hydrogen, so it's H3O plus. So this is what we do for the hydrolysis of HaloAlkanes. Water acts as the nucleophile. So it will attack the carbon during the halogen, and then the halogen will come off and the water will be attached to it. But it will not end there. You will do a second step. And next molecule of water will act as a base. And we know that bases are proton acceptors. And the proton is basically a hydrogen. Right? Right here, the OH bond is polarized. This oxygen is slightly negative, the hydrogen is slightly positive. So basically you're removing a proton. So when this hydrogen comes off, this oxygen gets both of the electrons. So this hydrogen is removed and this oxygen takes the electrons. So that's hydrolysis of your haloalkane. And you will do the same thing for the SN1 mechanism. So you can try the SN1. So it will be the same thing. Water is going to act as first we are going to form the carbocation, and then right here, instead of your hydroxide ion, water is going to act as a base. So that means it would be water. So step 1 stays the same for the SN1 mechanism. The carbocation will be formed. Water will do the attack. And so you will have OH2 here. Alright, so the water, it will be attached. And then now, draw this, and so water is going to act as a base. Move the proton, and you get this. And you have that. So that's it. We have 2 minutes left. So, if you are doing it for the SN1, step 1 will stay the same. The halogen will come off, we get the carbocation. Step 2 is our nucleophilic attack on the carbocation. Water is our nucleophile this time. So water will attack the carbocation. The bond will be formed. So in this one, we don't do any transition state. In SN2, in SN1, no transition state. So this water acts as a nucleophile, it attacks your carbocation, and it is attached to it. And then the third step, so with hydrolysis of HaloAlkane, you have an extra step. So normally SN2 is just a single step. When it's hydrolysis, it's 2 steps. Normally SN